welcome back to another exciting paper solving video. And in this video, we are basically going to discuss Unit 2 of October 2024. So this is your Edexcel chemistry tutor, Bokto Bhai. And so without further ado, let's get started. Moving on from section A, we have the first question, which is providing us a Maxwell-Boltzmann curve showing the distribution of molecular energies right here. We can see the energy progress and the fraction of the particles with a specific energy. They said, what happens to the curve when the temperature is increased? So whenever the temperature is increased, we see what happens, and that is the curve basically shifts to the right, and here the T2, when T2 here is obviously greater than T1, so basically the curve shifts to the right, and the activation the energy remains the same. There is no change, with the in activation energy when the temperature is increased. So the only thing that changes, we can see, is that the fraction of molecules containing or possessing energy greater than the activation energy, that number basically increases. As we can see, very clearly see that the green part the green part area for the red curve is higher than compared to the blue one. So if we use A, B, C, D, well, of course the peak will obviously become lower. That's one thing. But one thing is that the peaks, the area between both of the curves, if you say blue and the red, the area is going to remain the same, but the peak is going to decrease, meaning that even though less fraction of molecules will react, or the reaction is going to take less time to actually possess activation energy, but eventually more fraction of molecules is going to take in or possess energy greater than the activation energy. So we can say the peak becomes lower, and it's going to move further to the right. So that will be our real answer. Moving on, they said, how does the diagram change if a catalyst is added? Now, you should remember the thing that is, when catalyst is provided, the activation energy becomes lower. So in this case, obviously, if I see option A, the activation energy moves to the right. If it moves to the right, you can see logically it's wrong, because that would make the activation energy larger. But when a catalyst is added, the opposite happens. So we can say A is not the correct answer. If I move on to B, the activation energy moves to the left and the peak moves to the right. Now in this case, what happens is that there's no change in the peaks, because the number of molecules remains the same. As we all know, a catalyst will remain chemically unchanged. It's only going to decrease the activation energy by using a alternative route, and it's not going to change the number of moles, or the number of molecules, or the number of atoms of react, or the number of reactants, or the number of molecules which are going to go through during the reaction. So B is out of our option as well. This leaves us C and D. Now obviously D is incorrect, because we know the activation energy is supposed to decrease. It's not going to stay the same. So D is again automatically becomes irrelevant, which leaves us the only option as the correct answer, as with for us, is C, where the activation energy moves to the left and the peak stays the same. And this kind of makes sense, because obviously when it moves to the left, this signifies that the activation energy has decreased in its value. If we move on to number 2, we can see that the equilibrium between methane and steam is shown. You have seen that we have this reaction provided. We have methane and steam reacting with providing us an equilibrium reaction, in the end providing us carbon monoxide and of course hydrogen gas as a byproduct, while the forward reaction is endothermic as stated with this value right here. Now, what would be the effect of lowering the temperature? Now, when we lower the temperature, the what happens is that the first thing that happens is that the rate decreases, right? So this automatically makes A and B irrelevant, isn't it? So this leaves us C and D. Now, the decrease or the increase of yield solely depends on which side the equilibrium is going to shift. Now, we know that when the temperature is increased, the equilibrium will shift towards the endothermic direction. But in this case, the temperature is lowered, so obviously, since the forward reaction is endothermic, as I told you earlier, right here, so forward reaction is endothermic, so obviously we can easily state that the backward reaction is exothermic, right? So what we can say is that since the temperature is lowered, so the reaction, the equilibrium should go towards the exothermic side, in this case the backward direction. This means that the amount of product, in other words, the yield, is basically going to decrease. So that would make D as our correct answer. Moving on, what would be the effect of increasing the pressure? Now, when we basically increase the pressure, what happens is the rate increases, so we can easily cut off C and D as they both become irrelevant. So obviously now the next thing that we need to check, when we increase the pressure, the equilibrium tends to shift where there are higher number of moles. So if I talk about in the reactant side, we can clearly see that there are 4 moles, and if we see out in the product side we see 4 mole, but in the reactant side we tend to see 2 mole, isn't it? So that means what's going to happen is that the equilibrium is going to shift towards the left into the reactant side, considering there are less number of moles. So we can easily say that the answer would be B, because the rate increases, but of course the yield is going to decrease because the equilibrium is going to shift towards the left. Moving on, you have got some bond enthalpies provided, and I told you to find what is the bond enthalpy in kilojoule per mole of the CH bond. Now right here we can clearly see the reaction is provided. We can easily create an equation using this formula right here. We know that del 8 is equal to summation of energy released from the system or from the reactant side subtracted from the summation of energy released during the formation of the products. So the del H value is provided, which is about 206 right here. And if we can easily make a formula like this 4CH plus, we can clearly see that there is two molecules of water. So we can just multiply 464 with 2 times 464, and you have negative E out. Now, if we move on to the product side and we analyze it, we can clearly see there is 1 mole of carbon monoxide and, of course, 3 moles of hydrogen. So we can easily multiply this like this and add it up with 3 times 464. When you solve this and make CH the subject, you get about 415.7 kilojoule per mole, which is about approximately 416 kilojoule per mole. So our answer would be C right here. Moving on, we have number 3. Here it says, which equation shows the reaction that occurs when the standard enthalpy change of formation of carbon to carbonate is measured? Now, if you analyze 4 of these equations, you can clearly see down here, and that is very nice. You can see that oxygen here is not at its standard state, because we know that oxygen at its standard state is, a diatomic molecule. So we can say that A is irrelevant. If I talk about B right here, we can clearly see that the whole equation has been doubled. But when we tend to find the standard enthalpy change of formation, we tend to find the product produced is about 1 mole. So that is also irrelevant because the whole equation is doubled. Again, if I talk about C right here, we can easily see that copper and of course carbon, both of them are not at their standard states. So we know that the first condition during enthalpy change of formation is that the reactants must be at their standard states with 1 mole. So the only option that we're left with is option D. So option D is the correct answer, and it actually kind of makes sense. You can clearly see that all of them are at their standard states while a 1 mole of solid copper to carbonate is produced. Moving on, number 4, it states which statement about group 2 elements and their compounds is true. Now, if I talk about this one right here, calcium hydroxide is less soluble than magnesium hydroxide in water. Well, this is kind of is false because we know that magnesium, beryllium, magnesium, calcium, as we go down the group, what happens is that the solubility kind of increases. So it's kind of the opposite, that calcium hydroxide is more soluble than magnesium hydroxide. So yeah, A is kind of irrelevant. If I talk about B, if all group 2 metals provide a characteristic flame test, this is not correct because I can vouch for it because beryllium and magnesium don't show color. So that's not correct as well. If I talk about magnesium carbonate does not thermally decompose when heated. Now this is obviously not correct as well because it does, decompose when heated, and the reaction is somewhat like this magnesium carbonate, which obviously provides us magnesium oxide with carbon dioxide. This leaves us the only true statement is where the first ionization energy of magnesium is greater than that of calcium, right? So that will be the truth, and it is actually correct because as we go down the group, we can easily see that there's a decrease in the first ionization energy, and since magnesium is above calcium, it's going to have the greater energy than calcium. So we can say that our answer is D. Okay, moving on, we have number 5, a compound, which is a white solid, provides a red flame test and produces a colorless acidic gas when heated. What is the identity of the compound? Now, this is a very nice question. If you see number A right here, this seems to be the correct answer because they're told a colorless acidic gas is provided, and when we basically, decompose, when we decompose this calcium carbonate, we tend to get uh, acidic gas, which is basically carbon dioxide. So that's kind of correct. And if I talk about calcium night, and if I talk about the flame test, which basically, in other words, is the cation flame test. So here the cation is calcium, Ca2 plus, which obviously tends to provide a crimson red flame. So we can say that A and B is in our list. If I talk about C and D, you can see that sodium and strontium, these two are, you can say, are in our list. And but in sodium basically provides the yellow flame, while strontium provides strontium basically provide brown flame. So the only option here is A and B. And if I talk about that, when we basically, you know, heat off carbonate, we get the carbon dioxide, which is a colorless acidic gas. So we can easily say that we can easily vouch that the answer is A right here. Moving on, if I talk about number 6, which statement explains the origin of a flame test color? If I see all the options right here, uh, you have to understand that uh, the test color which is provided, it only happens when energy is emitted. So I can very clearly see that in A and C we see that electrons absorb the energy. Now that is not correct, so this makes A and C irrelevant, which leaves us B and D. If I talk about B, you can see that electrons are emitting energy as they jump to a higher energy level. Now that is not correct because electrons tend to emit energy when they return back from the higher energy level to their ground state or the lower energy level from which they have, initially jumped. So in this case, D is our correct answer. Moving on, number 7, sulfuric acid and sodium hydroxide is shown. You can see the reaction right here. They said which sample of sulfuric acid solution will be exactly neutralized by 20 cm cube of 0.5 mole of sodium hydroxide. Now, in order to solve this, we can clearly find the number of moles of sodium hydroxide right here, which is about 0.01 mole. Now we can clearly see that there is the mole ratio provided, which is about 2:1. So when 2 moles of sodium hydroxide reacts with H2SO4, we can use this mole ratio and find the exact number of moles of sulfuric acid, or in other words, sodium hydroxide. The amount of sodium hydroxide required, or the amount of sulfuric acid, which must be exactly neutralized by this amount of moles. So if we do that, we get about half times 0.01 down here, which is of course is equal to 0.005. Now 0.005 is the number of moles which will be the sample of sulfuric acid, which must be exactly neutralized by 0.01 moles of sodium hydroxide. So if we just basically use the trial and error method, that is if we find for this one, we get about 0.005 moles if we do the math and find the number of moles for this one right here. This and this is not possible, while this one also does not provide 0.005, so the only option here is A. Moving on, we have a 20-gram sample of iron 3 sulfate, which was dissolved in water. This told us how many sulfate ions are in the solution produced. Now, of course, you have the molar mass Fe2SO4 is equal to 400. We can clearly use this formula right here, where we can find the total number of sulfate ions using the number of moles of Fe2SO4 times the number of sulfate ions per formula unit. You can see there are three, per formula unit, times the Avogadro's constant, which is here provided. Now you know the mass, you know the molar mass, you can easily find the moles right here, which is about 20 divided by 400. So now if you do the math down here, you have exactly 0.05 mole. If we talk about the number of sulfate ions, it's 3, and if I talk about the Avogadro's constant, it is about 6 times 10 to the power 23 down here. So eventually, you can just write it down as 0.05 times 3 times 6.0 times 10 to the power 23, which will eventually lead us to 9 times 10 to the power 22. Sulfate ions. So we can say the answer is B down here. Moving on, we can see that which substance is formed when concentrated sulfuric acid reacts with sodium solid potassium chloride to be Xz. Now this is the reaction. You can see that when potassium chloride reacts with sulfuric acid, you tend to get one of the hydrogen ion being dissociated from H2SO4, being, reacting with, or along with the sulfate ion, one of them being dissociated and reacting with chloride, while the potassium, in other hand, reacts with the HSO4 minus, producing KHSO4 and HCl as a byproduct. So three of these are obviously not even are produced as byproducts. So the only product, which is KHSO4, matches with option D right here. So our answer is D. What is the color of the solution formed iodine dissolves in cyclohexane? Now, if I talk about this one, you have to understand that the color of iodine, basically. Now, when iodine dissolves in cyclohexane, we tend to get a purple color of iodine, because iodine, when it's concentrated, only then we get blue-black. In other words, you can say brown. But since obviously iodine here did not mention it's concentrated, so the only answer is pulpil. Gray is only said when the iodine is in solid form, but that is not the standard state of iodine. Yellow is not the correct answer because iodine is never shows yellow color. So the only option is C right here. They told us which alkane has the highest boiling temperature. Now, if I talk about hexane, pentane, if I talk about C and D right here, both of them are branched, and branched compounds tend to have a lower boiling point. So obviously C and D is out of the equation. This is just B and A. Now, pentane contains less number of electrons. So since there's less number of electrons, so less van der Waals force. So if there's less van der Waals force, well, obviously we can say the boiling temperatures compared to hexane is going to be lower. So obviously the answer would be A, which would have the highest Pauling temperature, considering it has it has no branch, and obviously it's a straight chain with the highest number of electrons among all the compounds right here. If I talk about number 12, we have what is the name of the alcohol shown right here. Now, since this said 3-ol, so we can start the naming 1, 2, 3, 4, 5, 6. Now, the only option that matches here is obviously B, so the answer would be B. We can see 4-methyl with hexane 3-ol. 1, 2, 3, 4, 5, 6. There are 6 carbons in the main straight chain, so the only answer is B. The others are not relevant with the diagram provided. Moving on, we have seen chloroethane react with aqueous potassium hydroxide to produce ethanol. They said what is the role of the hydroxide ion in this reaction. Now, when chloroethane reacts with potassium hydroxide, it basically goes via nucleophilic substitution reaction. Since it goes via nucleophilic substitution reaction, so obviously we can say that hydroxide ion right here is going to act as a nucleophile. Electrophile is irrelevant, and it also makes reducing agent and option D as irrelevant as well. So the only answer is B. So since I've already said it's the mechanism is nucleophilic substitution reaction, then we need to check out what happens and how does the nucleophile attack. Now A and obviously D right here is incorrect, because we can clearly see that the nucleophile is attacking the wrong guy here. It was supposed to attack the carbon atom, which is attached with the halogen. Now, if I talk about B and C, B is instantly rejected because we can clearly see that the nucleophile is attacking the wrong carbon. It is supposed to attack the carbon consisting of the halogen, so that when it attacks the carbon, for example in option C, which is the correct one, the bonded electrons present in the CCl gets taken away by the more electronegative atom, which is chlorine in this case, and this bond basically breaks down, producing our favorite carbon down here. And then again the OH again attacks so that it can produce the alcohol. So our only option here is C. Let's say the question is about 4 organic compounds. You're provided with 4 organic compounds. Which compound would not give a color change when heated with acidified potassium dichromate 6 solution? The only option here that would not react with acidified potassium dichromate 6 is a ketone, which is in this one is propanone. The others are going to react. This is an aldehyde, and we can clearly see that these two right here are alcohols, regardless of whatever their whether they're tertiary, secondary, they're going to react with acidified potassium dichromate 6 solution because it is an oxidizing agent. But you cannot further oxidize ketones, because when you oxidize alcohols and then you can produce aldehydes, which further if oxidized provides the formation of carboxylic acids. So D is our correct answer. It's not going to give a color change. Now, if we talk about which compound could give peaks at mass to charge ratio of 31, well, this radical right here in mass spectrum is going to have a mass to charge ratio of 60, and this radical is going to have a mass to charge ratio of 31. So my next question would be that how do you identify it? Now, if you look at very closely, propanone and propanol is kind of incorrect because both of them consist of double bonds. So it's kind of rather impossible to produce the oxygen atom from the double bond as they break through. So C and D is openly cut. If I talk about A and B, propan 2-ol and propan 1-ol, we can clearly see that this is connected with the first carbon. So obviously this is going to be absent. The CH2H plus is going to be absent in propan 2-ol, so which also makes B irrelevant. This leaves us option A as the only correct answer, which is propan 1-ol, and it does contain both of the radicals. You have CH2OH plus as well as CH2OH plus in propan 1-ol. So A is the correct answer. Our last question from section A is that an infrared spectrum for a compound containing one functional group is provided. You can see the transmittance and you can see the wave number. Which functional group is most likely to be present in this compound? Refer to your data booklet. Now, if I talk about right here, you can see the highest transmittance is about 1616. It's between, you can say, 1700 to 1800. Well, we need to check out what is there between 1600 and 1800. So that is, of course, we can clearly see that it is within the aldehyde, or there is the carbon to double carbonyl group, which provides these stretching vibrations between 1600 to 1714 or 1700 to 1800s. So we can say that this guy right here represents, or allows, or you can say identifies the presence of carbonyl group. So this basically instantly omits we can say this basically instantly omits, we can say, aldehyde. Can we say aldehyde? We're not sure about that. We need to check more. If I take out from here, you can see from 3000 to 3100, we can see that there is this transmittance, and we can see that this falls within the carboxylic acids group, right? And if there's anything else, we can also see that this is the one, and we can also see that it may be also alcohol and phenol. Main thing is that we can also signify that there is the presence of OH stretching vibrations as well. So this signifies the presence of OH group. Now, since both of them are present, so we cannot actually say that it is an alcohol or an aldehyde, not even ketone. It's only possible, since both of the functional groups are present, when we join them together, the only possible functional group is a carboxylic acid functional group. So our answer will be option C, down right here. With this, our section A is completed. Okay, moving on. Now we are going to start section B of October 2024. So without further ado, let's start. Number 16. This question is about magnesium sulfate, a white ionic solid that is very soluble in water. So you have the hydrated magnesium sulfates, which have the general formula magnesium sulfate dot XH2O, where X is the number of water molecules of crystallization. So we can see that a sample of hydrated magnesium sulfate was heated until all the water had been removed from the crystals, and the mass of the sample decreased from 6.92 to 6.04 gram. State how you'd ensure that all the water had been removed from the crystals. Now we can see that the 120.124 Fahrenheit, and how to do that, we can only do that by heating it to constant mass. That means we'll keep on heating the crystals, or the solution, until there is no change in mass. So we can write heat the sample until there is no change in mass. So that is basically the answer for this one. Again, they said calculate the number of water molecules of crystallization in X in the formula of the sample of hydrated magnesium sulfate. Now, of course, we need to at first calculate the mass in moles of water, which is, of course, the mass of water. You can easily calculate it by using the formula. You can see that the mass of the sample decreased from 6.9 to 6.04. So if you subtract it, 6.92 from 6.04 gram right here, we tend to get about 0.88 gram. So that's the mass of water. We can see that. Moving on, we can clearly see the next part, that we need to now calculate the moles. So the moles would be 0.88 divided by 18, which is going to provide us with 0.04889 moles. Now that is the mole of water. So now we know the moles of water. The next thing, we can now, calculate the moles of MgSO4. The moles of MgSO4, because we need to use the ratio of both of them in order to get the value of X. So if you calculate the MgSO4, which is about 6.04, divided by 120.4, the molar mass is provided above, as provided above. So we can easily start and find the answer as about 5.02 times 10 to the power minus 2 moles. So that's the moles of magnesium sulfate. Moving on, we can just use the ratio, 1:1 ratio basically. That is, say, why 1:1 ratio? Because we can clearly see that when the magnesium sulfate is heated, uh, the product and the reactant side tend to have a 1:1 ratio. So we can just easily divide it off. So we can just write it down as, of course, H2O dot MgSO4. So if you do the math down here, so you can just divide it off. You have 0.04889 is to 5.02 times 10 to the power minus 92. So eventually you get about 0.97454. That is the moles. So you can approximately write this as 1. So here the value of X is 1. That's the number of moles, which is represent the number of moles of water, which is represented in the sample of hydrated magnesium sulfate. Again, if you move on, the most common form of hydrated magnesium sulfate is this. Now, the student carried out 2 experiments. You can see that to determine the enthalpy change and the values. And in the first experiment, the student determined the enthalpy change when dissolving anhydrous magnesium sulfate. And the data is provided where you see the 100 gram of distilled water is placed in a polystyrene cup, and the temperature was recorded. The results were provided with the starting temperature, while 0.0628 moles of anhydrous magnesium sulfate was added. The mixture was stirred and the maximum temperature was recorded. Calculate the enthalpy change for this reaction, giving your answer to an appropriate number of significant figures. Appropriate basically means that you should provide it between 2 to 3 significant figures, and sign basically indicates the nature of the reaction. And units are obviously, you can give it between about kilojoule or joule per mole. So in this case, we're going to give in kilojoule per mole. So how can we find the enthalpy change? Well, it's pretty simple. We can use first we can find the amount of energy using this formula, an amount of energy, released using this formula, mc del T. Why am I saying this? Because the maximum temperature increased. So the temperature basically increased, basically heat energy was provided, and whenever something is provided, that means the nature of the reaction is exothermic. So we can just give a negative sign down here, and we can just start doing it. Now, since the density of the solution is 1 gram per cm cube, so we can consider the mass provided right here, which is about 100 grams. So you can just write it down as minus 100 times 4.18 times the change in temperature, which is about 29.4 minus 16.6. Eventually, you get about 85. You basically get about 5350.4 joule. That's the basically amount of energy, which you convert in kilojoule by dividing it by 1000. That brings us to 53, which is about 5.35 kilojoule. Later on, you can just find the enthalpy change of moles, the enthalpy change basically per mole, by dividing the number of moles with this one. So we know the number of moles is about 0.0628, so we can just divide it 5.35 divided by 0.0628, which will eventually provide us as 85.2 kilojoule per mole. Don't forget to provide the negative sign. That's the correct answer. Moving on, they said the Hess cycle. They told us to complete the Hess cycle. In the second experiment, he determined the enthalpy change when dissolving this, hydrated magnesium sulfate. This is the reaction. The nature of the reaction is provided, which is endothermic. And of course, in order to complete this Hess cycle, uh, the told enthalpy change in dissolving. So we can the common thing when we basically dissolve this, when you try to dissolve when you try to make it anhydrous, is that what when you try to decompose it, you tend to get one of the products as water and the other product is magnesium sulfate as it gets separated. On the other hand, when you try to basically, create an hydrated salt by, you know, adding them together by adding in the anhydrous salt or magnesium sulfate with water. In this case, also, you tend to provide the reactant as water. So the common product is going to be in both cases. You have water because we know that both of them are going to go through the enthalpy change of hydration. Now, the next thing that we need to find is, of course, the enthalpy change when anhydrous magnesium sulfate forms hydrated magnesium sulfate. So they told you to, in other words, find the enthalpy change of hydration down here, which is this value down here. Now you can easily do that by checking out the values provided. Now, when you do this, the value here is provided. The value here is provided as plus 15.8 kilojoule per mole. And when this reaction down here, we tend to find about negative 85.2 kilojoule per mole. So that will be negative 85.2 kilojoule per mole, the energy enthalpy change value from here to there. So as you can see in the first experiment. Now, secondly, if you want to now calculate this value down here, so you can just, if you want to find this one, that means that you need to go from this to this. So this value is going to become negative if we use our concepts of vector mechanics down here. So hydration is equal to, you can say it's negative 85.2 kilojoule per mole is going to be negative 15.8 kilojoule per mole, considering that we, in order to find this arrow sign has to be reverted to this part. Anyways, so when you do that, when you add them up, basically, the answer that you get is about negative 101 kilojoule per mole to be approximate. Okay. Okay. Anyways, now let's move on to the next part. Magnesium sulfate is very soluble in water. You draw a label diagram showing how both the magnesium ion interact with the sulfate ion with water molecules. Now, we basically know that in magnesium sulfate, the cation is Mg2 plus, while the anion is this one, SO2 minus. So what's going to happen is pretty simple. The cation is basically going to attract the oxygen atom, partially negatively charged oxygen molecules of water, something like this. And if I talk about the sulfate, it's just going to be the opposite. That is, the partially positively charged hydrogen ions down here. So like this, you can basically engulf the ions with the respected water molecules in the correct way. Barium ions are toxic in aqueous solution. If a solution containing barium ions enters the body, the barium poisoning occurs. Describe how drinking magnesium sulfate solution can reduce the extent of the poisoning. Now remember, what happens is that when you drink magnesium sulfate, what happens is that there's this crazy cool reaction. The crazy cool reaction is that the barium ions that enters that are responsible for poisoning, they basically react with the sulfate ions coming out from the magnesium sulfate, obviously with state symbols since they said, so that's going to be aqueous. and that's going to be aqueous as well, producing barium sulfate solid. Now that is a white precipitate. So what is happening here? We can write that the barium ions are being removed from the solution by precipitation of insoluble barium sulfate. As you can see clearly in this ionic equation, this is produced and abolished from the body. Hence, this will reduce the extent of the poisoning coming out from the barium ions that enter our body. Moving on, this question is about two halogenoalkanes A and B, which have the structures as shown. So they're told you to name the compound A. Now this is pretty simple since you can see that the longest chain here is this one. So it's 1, 2, 3. With the second carbon, the iodine is attached, so we can write as 2-iodo. We can also see a methyl group being attached, so we can say 2-iodo, 2-methyl. Since the longest chain has 3 carbons, so it's obviously propane. They're told to draw the skeletal formula of B. Now, this is pretty simple, so you can just write it since there are 1, 2, 3, 4. So you can say there are 2, and there's another one, and that's you give a chlorine, something like this. That's the skeletal formula of B. 1, 2, 3, 4 carbons with chlorine, and in the skeletal formula, we do not tend to show the hydrogen atoms, just like unlike the displayed formula. Again, describe what would you observe when separate samples of A and B are warmed with silver nitrate solution with aqueous ethanol. Now, with observation with A, we can clearly say since there's the presence of iodine, so obviously a yellow precipitate will be produced. So that's a no-brainer. And if I talk about with observation B, since there's the presence of chloride ions, so obviously it's going to be a white precipitate. Okay, now let's move on to the next one. Give 2 reasons why A reacts more quickly than B when warmed with silver nitrate solution in aqueous ethanol. Now you should remember that why it does is that we can see that A here is a tertiary alcohol. What do we mean by tertiary alcohol? We tend to see that the central carbon is attached with 3 other carbons. So when you omit, or when the iodine basically goes away, tertiary carbocation is produced. So obviously this is a tertiary halogenoalkane. In the case of B, we can see it's a primary one because obviously the halogen is attached with the first carbon. The first carbon is attached only with one carbon, no, not with any other carbons. So yeah, we can say first we need to state that A is a tertiary halogenoalkane and B is a primary one. And on the other hand, due to this, you can say clearly that this makes the Ci bond weaker than the CCl bond. So if it's more weaker, then the iodine basically can, take the electrons during nucleophilic substitution. When the nucleophile attacks, it can easily take the electrons more faster than chlorine from its bond. I mean, both's going to happen, but this is going to take more faster compared to chlorine when it breaks down. So obviously, the reaction is going to be faster for A compared to B. So we can say that the Ci bond becomes weaker than the CCl bond due to this, for which A reacts faster than B. So this is the descriptive answer. Moving on, write an equation for the reaction of B with an alcoholic solution of potassium cyanide. A, name the organic product. Now, for reaction B, we can see that what is happening. Here, this is basically reacting with potassium cyanide, so we can easily write it down as C4H9Cl plus KCN, providing you C4H9CN plus KCl. And obviously the name of the product is going to be, since obviously you can see that there are 5 carbons to be exact, including the carbon from the nitrile, so we can say it's pentane nitrile, considering there's the cyanide group present in this compound. Moving on, we can suggest why this type of reaction is important in organic synthesis. Well, it's pretty simple, isn't it? What is happening here? One extra carbon is being added, right? So in organic synthesis, it acts as a way of extending the carbon chain by adding extra carbons. So this is the correct answer for this one. Moving on, you have number 18. Here the student determined the molecular mass of an unknown volatile organic liquid X using the apparatus shown. So you can see the gas syringe was placed in an oven and the liquid X was vaporized after it was kept in the, it was kept inside the gas syringe using the hypodermic syringe. The results are provided. As you can see, the data is provided down here in this, table. Let's go to the question. They're told to calculate the relative molecular mass of liquid X, which has been inserted by the student in the gas syringe. Now, in order to calculate this, at first let's convert the temperatures here provided. Now, the temperature at the oven, if you convert it into kelvins, you get about 368 Kelvin, which is pretty simple. You just add 95 plus 273. Okay. The next thing, if you want to, we need to convert the kilopascals to pascals, which is about 99,000 pascal. You just multiply 1,000 with 99 because we know that 1 pascal is equal to, actually, sorry, 1 kilopascal is equal to 1,000 pascal. Okay. The next thing we need to do is that we need to convert the volume right here to the SI unit meter cube. So in order to do that, all you need to do is that divide 81 with obviously 10 to the power 6. Okay, so if you do that, you tend to get about 8.1 times 10 to the power minus 5 meter cube. So moving on, if you write the values again, so we have the volume as 8.1 times 10 to the power minus 5 meter cube. Then you have the pressure as 99,000 Pascal. The temperature, of course, as 368 Kelvin. And we literally know the gas constant as well. So now to find what? If we can find the number of moles, then we can easily find the molecular mass, right? So we can just rearrange the equation as PV by RT, which is pretty simple. You can just plug in all the values, required values, something like this. And if you calculate down or plug it down on your calculator, all the values correctly, of course, you get about 2.622 times minus 3 mole. Now, to find the molecular mass is pretty simple. We know to find the molecular mass, all we need to do to divide the mass with, of course, the moles here provided. Now, we know the mass is 0.12 grams down here. with 2.622 times 10 minus 3. If we divide that, we tend to get our mass, which is about 45.763 gram per mole. So that is the molecular mass of liquid X. Moving on, if we move on, each molecule of X contains carbon atoms, hydrogen atoms, and one atom of oxygen. Identify X by name or formula using your answer from A. They said each molecule of X contains carbon atoms, hydrogen, and one atom of oxygen. So this is only obviously, I mean, if this is the case, and we obviously, they provided us this sort of stuff, so the only possible answer we can say, I mean, by checking out everything, so we can say it's ethanol. Because when you basically find the molecular mass, it basically corresponds to the calculated value above down here. So ethanol is the correct answer, or the correct identification of X. Again, number 19, this said the question is about group 7 halides. The increasing the boiling temperature, you can see the hydrogen halides is due to the London forces. Now they're told how the London forces, arise. At first, you need to understand that, these molecules, as you can see, hydrogen and chlorine atoms, they tend to produce temporary dipoles between them. Temporary dipoles basically means that since they're non-polar, since this is polar, bond, uh, partially positively charged is produced in the hydrogen atom, while partially negatively charges are produced in the chlorine atom. So this literally makes the whole thing, this produces a temporary dipole and makes this a dipole being produced down here, uh, something like this. So due to the production of this temporary dipole, the electrons, uh, have a random arrangement. Basically, the electrons, disorient among themselves, and the arrangement becomes random. So due to the asymmetrical distribution of the electrons, again this produce induced dipoles, and due to the production of induced dipoles, at the end the London forces arise. So we can write that since all the HX bonds are polar, they tend to produce temporary dipoles within their bonds, which leads to asymmetrical distribution of electrons within these bonds. If you basically draw the electron density map, you'll be able to see that more of the contour lines are present towards the chloride side, in the chlorine side compared to the hydrogen side, because obviously chlorine has a higher electronegativity compared to hydrogen. So we can say that within these bonds, these lead to the production of induced dipoles among other containing the HX bonds. So basically what they're trying to say is that since a temporary dipole is produced, another molecule consisting of this bond is basically going to produce induced dipole. Basically, the dipole here is going to induce a force of attraction to another dipole from another molecule of the same type. And this induced dipole is going to give rise to van der Waals force, or in other words, London forces. State why the London forces in hydrogen iodide are stronger than those present in hydrogen chloride and hydrogen bromide. Well, the simple answer is that hydrogen iodide has more electrons. So we can say that hydrogen iodide has more electrons, because we know that with the increase of electrons, the amount of London force, or the strength of London forces, increases. So the boiling temperature of hydrogen fluoride is plus 20 degrees Celsius. State what causes hydrogen fluoride to have such an unusually high boiling temperature. Well, first of all, hydrogen fluoride, apart from having London forces, it also tends to have the strongest intermolecular force, which is the hydrogen bond is also present in this compound apart from London forces, which is the strongest intermolecular force. Next up, chlorine reacts with water is shown. Now this is the reaction provided. Explain why this is a disproportionation reaction by referring to relevant oxidation numbers. Okay, first of all, you can clearly see that the chlorine is once oxidized and again it's reduced. You can see that clearly. So first of all, the chlorine is being oxidized, forming HOCl, and again it's reduced. Now what's the oxidation change? You can see here it is 0, here it is +1, and on the other hand it is of course 0 in the first place, and in HCl it's about -1. So we can easily say that the oxidation number is increasing. In this case it's being oxidized, and vice versa is happening for HCl. So we can write that here the chlorine species is being oxidized and reduced at the same time. So if that's the case, what is the proof? So you can see chlorine is oxidized, forming HOCl by changing oxidation number from 0 to +1. Chlorine is reduced to HCl by changing its oxidation number from 0 to +1. So this is the correct way of writing this type of answers. Again, state and explain what happens to the position of equilibrium when sodium hydroxide solution is added to this equilibrium mixture. Now, it's pretty simple. The equilibrium is going to shift to, obviously, to the right side, because we can clearly see that what happens is that particular solution with sodium hydroxide is added, it's going to react, with HCl down here. So yeah, so since it's going to react with HCl down here, so the overall product concentration is going to decrease, allowing more reactants to react and allowing favoring the forward reaction. So we can write down as the equilibrium gets shifted towards the right to make more HCl as any which would react with HCl when added. Okay, with this our section B is complete. Let's move on to the next part. Okay, section C, number 20. Now this question is about lithium and some of its compounds. Lithium has an atomic number of 3 and it's least of all the dense solid elements. Now, lithium hydroxide solution can be made by reacting with lithium with water. Write an equation for the reaction that offers. Now that is pretty simple. Since they told us to, include the state symbols, we just include that. With water, we get about lithium hydroxide aqueous, and the only thing that's left is hydrogen gas down here. Obviously, we need to give half in order to balance the whole thing. I'll give two observations. Now, since obviously hydrogen gas is produced, we can easily say that effervescence takes place. Effervescence basically means, bubbles or fizzing. Effervescence, we can say effervescence takes place. That's one of the observations we can say. Second observation, we can say that the solid lithium disappears, or you can say it floats on water as the reaction progresses. Whatever you want. Secondly, lithium metal is stored under oil. When a piece of lithium metal is removed from the oil, the surface quickly tarnishes. One compound formed is lithium nitride. State how lithium nitride is formed. Now this is pretty simple. What happens is that lithium reacts with nitrogen. Now where can we get nitrogen? We can only get nitrogen from the air because it's really abundant in amount. So from the air to produce, obviously, Li3N, lithium nitride. Now, the next one is a very nice question. We can see that mobile phones rely on rechargeable lithium batteries. The cell of one type of battery consists of an anode containing a compound of lithium and carbon and a cathode containing cobalt 4 oxide. The two electrodes are kept apart by a separator. We can see that. Now, when the cell is in use and the current flows at the anode, the lithium atoms lose electrons and form Li plus ions. The ions travel to the separator, and the electrons travel through the external circuit to the cathode. As you can see, this is described, and these are the reactions happening in the respective electrodes. Give the overall equation when the cell is being used. Now, if you cut down the electrons from the half ionic equations, the elements that are left are C6Li plus cobalt oxide, giving us, of course, giving us LiCOO2 plus C6. Now that is balanced, so we don't have to talk about that, and they never told you to give the state symbols as well. Again, The next question says, describe with reference to oxidation number what happens to cobalt when the cell is in use. Remember, when the cell is in use, reduction of cobalt takes place because we can see that the oxidation number of cobalt changes from +4 to +3. So we can say clearly reduction of cobalt takes place as its oxidation number changes from +4 to +3. Moving on, suggest one property the separator must have to ensure the lithium battery is viable. Now, viable basically means that the battery must work. So what's the one property the separator must have? Now, if the separator is not permeable or porous, the lithium ions won't be able to pass through during the reaction. So we can say very clearly that the separator must be porous for allowing Li plus ions to pass through during the reaction. Next up, lithium is often added to aluminum to make aluminum-lithium alloys. Now, of course, these alloys have a variety of uses, including aircraft manufacture, and one alloy contains only aluminum and lithium. It contains 2.45% of lithium by mass. Calculate the molar ratio of aluminum is to lithium. Now, of course, we can just easily calculate the moles of lithium since the percentage is provided by mass. So we can say lithium moles is 2.45. The molar mass is 6.9. So that basically sums up to 0.35507 mole. On the other hand, if I talk about percentage mass of aluminum, since they provided the percentage in a percentage, so we can say that out of 100, if we subtract 2.45, we will get our eventually the aluminum mass. So we can say that aluminum moles is nothing but 100 minus 2.45, and if you divide it, if you basically divide it by 27.0, which is the molar mass, you get about 3.6130 mole. Now, if you divide both of them, obviously you should divide the aluminum mass, 3.6130, divided by 0.35507. You can write this in the ratio form, which is about 10.175 is to 1, which is, if you round it off, which is 10 is to 1. So the molar ratio of aluminum is to lithium is 10 is to 1. So that's the reason why this alloy is better than pure aluminum for aircraft manufacture. The straight answer is that the alloy becomes the alloy the alloy makes the aircraft body much stronger than pure aluminum, because in pure aluminum we're just going to get the metallic bonds, but in case of an alloy we are going to have multiple types of bonds, such as the ionic bond, covalent bond, apart from having metallic bonds. So that would in overall increase the strength of the aircraft body. So yeah. Moving on, we have compounds of lithium group 1, and of course, you can say that compounds of group 2 have similar properties. Explain why the ionic ready of lithium plus and magnesium 2 plus are similar. The thermal decomposition of lithium nitrate is similar to that of the magnesium nitrate, but different from, from the thermal decomposition of sodium nitrate. Now, you should check out these two lines. Why? At first, let us tackle this point down here. When it comes to 6-mark questions, we must tackle the answer by, tackling the points given. First one, they said the ionic ready of lithium plus and magnesium 2 plus are similar. This basically means why? Why is that the case? This is because pretty simple. Magnesium has an extra shell than lithium. Yeah, that's a no-brainer. And as the charge on magnesium is Mg2 plus and Li plus in lithium, the ions in overall have similar ionic radius. Yeah, that is of course a no-brainer because both of them fall in the, within the same, one of them have one extra shell basically. So that's a no-brainer. The ions will be have similar size, considering that when two electrons get lost, so one shell is going to get, you know, taken away from magnesium, and that's going to basically that's going to be equal to the number of shells present in lithium. So first of all, that's the reason why basically Li plus and Mg2 plus have the similar ionic radius. Moving on, if I talk about the second point, the thermal decomposition of lithium nitrate is very similar to that. How can we prove that? At first, write the equation of thermal decomposition of lithium, lithium or magnesium nitrate, whatever you say. You can just give for like, okay, let's give lithium nitrate for instance. So for lithium nitrate, it's pretty simple. You have you have about 4 Li NO2, giving us 2 Li2O plus 4 NO2 plus oxygen. So that is the thermal decomposition for lithium nitrate. And if we compare it with the thermal decomposition of sodium nitrate, thermal decomposition of sodium nitrate, what do we have here? Well, we basically tend to have about sodium nitrate being decomposed to give sodium nitrate plus oxygen down here. Okay, so what is the differences and what are the similarities? We can clearly see that lithium and magnesium nitrate produce nitrogen dioxide, right? But sodium nitrate does not. If you basically write the thermal decomposition of if you basically write the thermal decomposition of if you just copy this, sorry, if you just write the thermal decomposition of magnesium nitrate down here, so we can just say that what we can just say that the thermal decomposition is about, again, magnesium nitrate, giving us you can say MgO plus nitrogen dioxide and oxygen. That is about 2, and that is about 2. So what are the similarities? You can clearly see that nitrogen dioxide gas is produced for both of the reactions, which is kind of not common for the decomposition of sodium nitrate. So we can say that lithium and sodium, sorry, magnesium produce nitrogen dioxide. Okay, you can see that very clearly. But what is not produced in the case of sodium nitrate? That nitrogen dioxide is not produced. So we can write that, but sodium nitrate doesn't produce that. Exactly. Now, why is that the case? It's the sole reason is that the sole reason is that you can say that this is because you can say both. You can say both of them. This is because magnesium 2 plus and lithium ions are you can say both of them to be you can talk about lithium. So if you talk about lithium at first, it would be better. So you can say this is because lithium ions are smaller than Na plus ions. So this literally means, as we know, according to the Fajon's rule, that we know that charge density, we know this crazy formula that R square charged by R square. So if you use this concept in our brain, so since the ions are smaller, that means the charge density of lithium will be greater than sodium. So we can just say this means Li plus will have a greater charge density than sodium ions. Since it is a greater chance, greater charge density, so it will tend to polarize the radical nitrate ions more, causing Mg2 plus and Li plus to decompose in a similar manner. So that is the reason why, due to the higher polarizing power of lithium ions and sodium and magnesium, both of them basically will decompose and produce the products in a similar manner. So with this, we can clearly say that our section C is also complete. So that's it for today, guys. Hope we can meet in another video with another exciting paper to be solved. Bye bye.